Hello everybody. We're in the beginning of July of 2023 and today I would like to talk to you about my paper called Residence Time versus Adjustment Time of Carbon Dioxide in the Atmosphere. This was recently published in the journal Entropy, and you can also find a copy there in this journal because it is open access. You can also find a link to it on my own homepage, stalinga.org. You'll find it there on the publications. And if you're familiar with this system, you can also find it in the Department of Information with a number that is given here below. And of course, I will make a link to this video below this video. Now, I suppose that that you know that we seem to be having some climate problem where our carbon dioxide that we are emitting into the atmosphere because of fossil fuel burning, this carbon dioxide is allegedly changing the climate. Now, for that to study this correctly, we should, of course, also have very good definitions of the concepts in this modeling. Otherwise, our entire reasoning will lead nowhere. And there seems to be a lot of confusion about the simple concepts. So today I'm going to explain these concepts to you. Specifically, and actually only, I'm going to talk to you about the difference of residence time and adjustment time of this carbon dioxide in the atmosphere. Now, the residence time we can think of is the average time an average molecule spends in the atmosphere, or the box that we have under consideration. I'm going to make it very simple today so that you will understand the concepts. That first we have here, let's say, a box that we call the atmosphere A, and in that we have our carbon dioxide molecules, and every now and then molecules can go then disappear from the atmosphere, and where they don't go to, this is not very relevant at the moment. We just call it that they are disappearing from the atmosphere, and we call this a sink or S. So every year a certain percentage of the molecules that are in the atmosphere, they go into the sink, and a certain percentage, a different percentage probably, or actually that is, a different percentage goes of the molecules that are in the sink, they go to the atmosphere. So now imagine that you have 10% of the molecules in the atmosphere every year they go to the sink, and 20% every year they go from the ones that are in the sink go to the atmosphere. And then of course when you have an equilibrium, so then 20% of this must be equal to 10% of this, meaning that we would have twice as much molecules in equilibrium as we have in the sink. In general, this looks very much like a simple first order chemistry reaction, so we can apply here the chemistry kinetics equations. So what we basically have, we have molecules A that can convert into molecules S, and molecules S can convert into molecules A, and both have reaction constants, which is basically the fraction of the molecules that go from the atmosphere to the sink, and from the sink to the atmosphere. This is complete classic chemistry equations. So the idea is that this is then the residence time, the average time it spends in a box, but the adjustment time is how long does it take to reach a new equilibrium. Imagine that, now let me put here a different color, that we're going to add here, we're going to add now our CO2 from fossil fuel emissions. Then there are two questions. What will be the new equilibrium value? One, and two, how long does it take to reach that equilibrium value? And that second concept is called the adjustment time. Now the idea is, according to the big references like the IPCC, that whereas the adjustment time can be short, the residence time can be short, the adjustment time is in the order of centuries. And why is this important? Because if the adjustment time is very short, in that case, then if we emit CO2 into the atmosphere, this CO2 is captured way too fast and will not do any effect, will have no effect on much on the climate. It simply doesn't have time enough to act on it. And the equilibrium value is reached very fast. So this paper is basically first about that the first part I'm going to explain what is the difference between residence time and adjustment time and show you that the adjustment time can never be longer than the residence time, which might come as a little bit as a surprise, but it is so. That is really chemistry kinetics. And in the second part I will then explain if now once we have shown that this is the case, what are the implications on the atmosphere and how much of our carbon dioxide is still in there and other things like this. So let's get started. First of all, a certain Solomon wrote a book. He was called The Deniers, and that is because he's a climate denier, and has shown that actually a lot of people have measured the residence time of carbon dioxide in the atmosphere. How that this will be done will be shown in a moment, namely by the atomic bomb tests that were done in the 50s. And he concluded that he put a summary, which I will show you also in a moment, that this is about 10 years. And if then the adjustment time would be 10 years, or in that ballpark, then that would undermine the prime tenet of the anthropogenic global warming hypothesis, because then a molecule will not have time to contribute to any greenhouse effect. It is like the water. When we burn fossil fuels, we also produce water. But the water, of course, it disappears in a couple of days. So it will have no time to change the climate, although the greenhouse effect of water is orders of magnitude bigger than carbon dioxide. So if the adjustment time is very short, then the products that we're doing, CO2 and H2O, will not have any effect on the climate. Even the IPCC is admitting this. Now, but then people say like, yes, the residence time is very short, so this goes very fast. The carbon dioxide atoms go very fast out of the atmosphere, but because they are compensated by a very big flux from the sink into the atmosphere, the net balance is rather small, so any perturbation that we have here will take a long time to establish. But this is against chemistry kinetics. But this is how Cawley is actually saying it. Natural fluxes into and out of the atmosphere are closely balanced, and hence comparatively small anthropogenic fluxes can have a substantial effect on atmospheric concentrations. Well, this seems intuitively you think this is correct, but this goes against chemistry kinetics, as I will show you. First of all, we have to show that the IPCC is actually really using this first order two-box models, simple chemistry, because as they wrote in their own IPCC, the latest IPCC report, I have here a draft version, but I guess it's still the same, I didn't even check. But there they wrote, turnover time, that is residence time, turnover time is the ratio of mass of a reservoir and the total rate of removal from the reservoir. So let me write this then here. Turnover time, tau, let's call it tau, is the ratio of the mass reservoir, so A, divided by the flux that goes from A to S. So I could write here A to S, but I call it, if I'm not mistaken, N minus. It is the one where it is going out. It is reducing the amount of carbon dioxide in the atmosphere. Now, and they also say that the adjustment time or response time is the time scale characterizing the decay of an instantaneous pulse into the reservoir. So that means that if we change here A, maybe because we are making a step, we inject a certain delta function of A into the atmosphere, and then of course it will reach a new equilibrium, not necessarily the original one. This can be, this level can be different than this level. So how long, what is the characteristic time of this transient? That is the adjustment time. And that is to characterize the adjustment of mass reservoir following a step change, so that's what I say here, or delta function or something like this. So when we perturb or disturb the system, how long does it take to restore a new equilibrium? So now we're going to discuss the difference of these two things, and we will show that the hypothesis that the adjustment time can be longer than the residence time is mathematically is not possible. Or in other words, what Mr. Cawley says here, that is simply, that's nonsense. First of all, let's show here the table where Mr. Mr. Solomon, he presented it, he published it in his book. You can see here the residence time of carbon dioxide in the atmosphere, and it's all of the other 7 years, 10 years, 7, 5, 10. It's apparently, it's not so simple, so you get a lot of people and they're presenting a lot of different values. But the idea is that it is rather short, let's say the order of a decade. Mr. Solomon here puts it, let's say, 10 years or something like this. The IPCC is using 4 years in their own report. They wrote that it's 4 years. I will give them a sort of like still a margin of error, and I will use 5 years also because it is then things are easier to calculate and you can more easily follow. So let's get started with the kinetic model. We have here the two-box model. I hope you're right. Yeah, I have here a figure. We have the two-box model. You have two boxes. You have the atmosphere and all the rest that we call the sink. And we use first-order kinetic, meaning that the flux from one box to the other is proportional to the amount that is in that box. So from the atmosphere to the sink is proportional to the amount in the atmosphere and then divided by this constant, because it is the inverse of this function. The flux is the concentration in the atmosphere, or the amount in the atmosphere divided by the time constant. We call this the atmospheric residence time tau A. And from the sink to the atmosphere, we call this the flux Fn plus, because it increases the amount in the atmosphere, and that is the amount in the sink divided by the residence time in the sink. I also put here the values that are known. This we can measure quite well. In the atmosphere we have at this moment 420 parts per million in the atmosphere carbon dioxide, and this translates into a total of 3,403 gigaton. Also I put here this flux, that the human flux that is then into the box that is added to it, that is 38 gigatons per year is injected into this system. Now we can make a solution to this. If we perturb the system, we will reach at the end a new equilibrium value. This equilibrium value was the starting equilibrium value, so before we perturb the system, times how much we perturbed it, and then the ratio of these this residence times, or actually the ratio of the residence time in the atmosphere divided by the sum of residence times. What is more important for us is, so that is the end value. That is the end value that we get after perturbing it. More important for this discussion is how long does it take? For that we just solve the equation that we have here. We just have a linear equation, differential equation, and we can solve this. The change in the atmospheric concentration is the difference between the fluxes, and if we solve that, we get something like this, that this the change, the time change, the derivative of the concentration of carbon dioxide in the atmosphere is the difference between the final value and the actual value multiplied by the sum of reciprocal residence times. So notice very well that the solution of this differential equation is an exponential decay, reaching finally a new value, and it is doing this with a time constant given by the reciprocal sum of the two time constants. This reciprocal sum then is 1 divided by tau, that is the adjustment time, is 1 divided by the residence time in the atmosphere plus 1 divided by the residence time in the sink. And note that this adjustment time then is always shorter than these individual residence times in the atmosphere and in the sink. The adjustment time is always shorter than the adjustment time. The adjustment time of the in the atmosphere is always shorter than the residence time of carbon dioxide in the atmosphere and the residence time of carbon dioxide in the sink. That's very important to know. So imagine, for instance, if the residence time in the atmosphere is 10 years and the residence time in the sink is 100 years, then the adjustment time, how long it takes to establish a new equilibrium, is 9.1 years, and that is shorter than the residence time. It sounds maybe a little bit strange, but you can solve this equation yourself, and it is actually classic chemistry kinetics. I've made here a simple solution. I start with 100 units of carbon dioxide in the atmosphere and in the sink, both of them, they have 100, and I put the residence times of the atmosphere and the sink, I put them equal, and therefore I have it's in equilibrium. I have 100 molecules in the sink, and I have 100 molecules or moles, if you wish, in the atmosphere. And then I perturb the atmosphere, I add 100 to it at time equals 0, and then you can see that it is with exponential decay, it reaches a new equilibrium value, where again the amounts of carbon dioxide in the sink and in the atmosphere are equal, but they are now at 150. And the time it takes, I've plotted it here. Here are the residence time. I have taken it as 1,000 iterations, and you can see that the adjustment time is in the order of, not in the order, is exactly 500 iterations. That's an example that I've given here. I can also put the adjustment time then, I can plot the adjustment time as a function of the residence time. Imagine that the residence time in the atmosphere is 1, and now I'm changing here the sink residence time. And if the sink residence time is 0, then the adjustment time is actually also 0. And only when the residence time in the sink is infinite, then the adjustment time is equal to the residence time in the atmosphere. So the conclusion here is something very important, that the adjustment time of how fast a perturbation actually reaches, is processed, that the system is reaching a new equilibrium, is actually shorter than the residence time in either sink and atmosphere. Okay, and then there are other people that are using the same reasoning as this, what was it, Cawley, that says that, yeah, but it's about the balance between the two is very, very narrow. So that means that it takes a long time to adjust perturbation. So this is not true. This implies that you would have a 0th order kinetics, meaning that the fluxes are independent of the concentrations in the atmosphere in the sink. And that is a very strange, that would be a very strange, difficult to imagine situation. And even the IPCC, the way it's describing here, they say themselves that they're using a first order exponential decay process. And a first order exponential decay process, then the fluxes are proportional, linearly proportional to the concentrations or to the quantities in the boxes. So the IPCC is using first order model, and I show you here in a simple 2-box model that in this case the adjustment time is shorter than the residence time, but when the residence time in the sink is very high, which indeed is the case, then the residence time is closely, just slowly below, but closely close to the residence time in the atmosphere. So we could expect that the adjustment time of carbon dioxide in the atmosphere, in fact, is, let's say, according to Solomon would be 10 years, and according to me would be, let's say, 5 years, and according to the IPCC it would be 4 years, and that means it's game over for the climate change model, our carbon dioxide has no effect on the climate. That is a very important conclusion. The IPCC, in the way that they write this, that they use a first order exponential decay process and they use turnover time and adjustment time. They basically, in this page 1457, basically they kill their own climate model. Okay, let's see if I still want to say something more before I go to part 2. I will write then another video where I will then say like, well, okay, so what if the adjustment time is 5 years or short like this? What will be the implications of the data? Down in the next video, I'm going to use the exact data and tell you that there is something wrong with this data. It is not consistent with some ideas that are circulating in society. So I hope you enjoyed this video, and see you in the next one where I will talk about some scenarios. See you then.